Okay. So I guess in order to minimize what the missing 1/3 of the class is missing by not being here. I mean, I know we can always go back and watch the video later, but how is the homework coming along?
I'm just excited I finally got the first part of 2 done. Have I looked at the other parts? No, but I got some of it done, so I'm just happy with that.
I've got 1 and 3 done, and I've got like about half of number 2 done.
Okay.
I don't know the specifics. I think I'm probably where Samson was, where I had started a lot of them, but not necessarily finished. So.
Okay.
That's my next couple of days.
Okay. Well, I mean, you know, you've had a really big thing to deal with lately.
Yeah.
and that only very recently was shoved out of the way. So that's perfectly fine. Okay. So. Caitlin, how about you? And I know you joined later, but.
Yeah, I haven't made super great progress, but I'm getting there.
Okay. So, well, and plus you had a big thing from my class, so it also only recently was polished off. So, okay. All right. Well, so do any of the 4 of you have questions at this point?
Is there anything special we should know about doing 2A for making the Taylor series expansion? Okay.
All right, and that's to confirm that it's second order accurate. Mm-hmm. Okay, and I assume that like you're also looking at the hints document that has.
Yes.
Okay. Let's see.
I want to make sure there's like not any other little trick I need to know.
It's nothing special in this case.
Okay.
Because, like, since you're, okay, well, I guess in the interest of being thorough here, because what you have is you have a system of equations that you're solving, and each row of that system describes the approximation to the PDE at a particular point, like, you know, xi. So,
I found this answer.
Okay, well, thank you. So approximate second derivative at xi or minus that equals f of xi. And then you're doing Taylor expansion on that center difference. And I have no interest in like dealing with boundary conditions or anything like that. You can just focus on just a generic equation from this system.
Okay.
So you just Taylor expand whatever's in the center difference, u of xi plus h, u of xi minus h, and then, and like a hint say, take into account that when you're Taylor expanding, your u is the exact solution, so minus uxx really does equal f. Also take into account the definition that this is from the notes of local truncation error. Mm-hmm. And just to be precise about that, okay, that now is equal to a u hat minus f, where this is the exact solution. So in this problem, Since A is the matrix that comes from discretizing your PDE, you have minus second derivative applied to the exact solution minus F. So because the computed solution would satisfy this exactly with 0 on the left-hand side. The exact solution does not, because this is not the PDE, this is spatially discretized PDE. So the exact solution satisfies this equation with not 0 on the left-hand side, but local truncation error on the left-hand side. So you do tailor expansion, you simplify this as much as you can, and what you get is your error term, which ought to be, so all of this should be or h squared. And then you can say, oh, the local truncation error is or h squared. So if U with an ordinary vector symbol is your computed solution, U hat represents the exact solution but evaluated at the grid points. So a U computed solution equals F, and then a U hat equals F plus tau. So that's the relationship between the two. You can think of two different ways of trying to analyze error that you can think of opposites of each other. One of them is shown here. You substitute the exact solution into the numerical method. What would the opposite of that be? The opposite would be you can plug the computed solution into the original problem. Like, so the computed solution into the original PDE. The problem with that is the PDE works with functions of x, continuous functions, or functions defined on a continuum. The computed solution is just a vector of grid points. So the only way to substitute that into the PDE would be to like maybe do some interpolation or something to go from those grid point values into a function defined on a continuum. But one could try that, but it's far easier to do this. Take your exact solution, which already is a function, evaluate it on the grid. So basically, you're like you're discretizing your exact solution and plug it into here. So that's why this route is used for error analysis. It's certainly easier than the other way around, because the ultimate goal is to determine as your discretization becomes finer and finer, as your grid spacing h goes to 0, does your computed solution on the grid really approach the values of the exact solution on the grid? And this is not the whole process. This is just local truncation error, and ultimately you want to get the global error, but it works. This may sound like overkill, but I'm making a big deal out of this just because this approach to error analysis is used in so many different settings for all different kinds of PDEs. Like if we were to look at, for instance, time-dependent PDEs, And so schemes that would combine this kind of finite differencing in space with a method of solving a system of ODEs in time, like the time stepping method. So the numerical scheme has a very different appearance. But the philosophy or the approach to error analysis is exactly the same. Local truncation error in whatever setting you're dealing with is always obtained from substituting the exact solution into the numerical method. Stability is always about ensuring that a small change in the problem data does not lead to an arbitrarily large change in the solution. You always have this notion of, if you have established consistency, like your local truncation error goes to 0 in whatever sense, and then stability, and you have convergence. So regardless of setting, it's important to have that framework in your mind so that if you come across a problem that you haven't really done error analysis before, but you have done it for other problems, that you still want to think within that same framework so that you can use the same ideas. Okay. Any other homework questions that I might digress from? Number 3. Okay.
Instead of investigating the accuracy of the numerical solution to obtain, one is to do a table expansion of this using MATLAB to build a parallel.
Okay. For that one, I'm fine with examining it numerically, like seeing what happens to the error as h goes to 0. Is it, what order of accuracy do you see? And one could do iterative expansion, but you guys get to suffer through that elsewhere. Any other?
For C, I still have not figured out how to make that, because we're expecting the error to go back into the front line.
Right. Oh, right. Is that one that you showed me earlier?
Yeah.
And at a time, it didn't seem like it was quite 4-4 accurate, but you got it to work?
No, it hasn't worked.
Oh, okay. Okay, but that was 2C?
Yeah.
Okay, and that's the one where you're doing the
Defend correction.
right. Okay. All right. Oh, no one else has gotten that far, right? Robert, I don't know if you have dealt with that one.
2C, I've started on it. I haven't
Okay.
finished 2C yet.
Okay. I just want to see if anyone else is in the same boat, but.
Around on Thursday.
Sorry, what?
We came around on Thursday.
Right.
We ran around.
Yeah. And yeah, at the time, I didn't recall seeing anything in particular that might have been wrong with the code there. Okay, so what's something like where certain things were fixed and these got an accurate solution, but still not accurate enough?
Yeah.
Right. Okay, so what that would suggest is the scheme that you have ends up having an error term, like a leading error term that is still order h squared. But I think it's what the order of accuracy was looking like. So for some reason, because what's supposed to happen is that error term is supposed to cancel out and leave you with fourth order. So it could just be something having some kind of scaling factor or sign that's off. Actually, one thing I'm wondering here from the previous times where I've done this class, if I have that, okay. Okay, and that's problem 2C. There's B. So I have code from there's actually Carly's from when she took class a couple years ago. Okay. C is A, V, errors V. Part C. Okay. Okay, so in the fourth order scheme, okay. Oh, okay. What's interesting in this case, the code is close to fourth order. It's not quite there, but like order of accuracy, like 3.5. So certainly better than second anyway. What's second order that your code appears to be getting? Okay. I guess the easiest way to check is if you're you're cutting H in half, is the error decreasing by a factor of 4, or is it closer to 16? Like in this case, and I haven't checked Carly's code to see if it's incorrect or not. Like a ratio is like 11, because a ratio of 8 would be third order accurate. Okay, so but yeah, because I know that you were accounting for the boundary values. Okay, so that's something we may have to take a look at later. See what's going on with the code, but yeah, that's one thing to check. Like if you choose choose n, the number of grid points to be like a power of 2 minus 1. So that way you're always cutting your h in half every time you use a larger power of 2. And then welcome. So then see what's happening with the error. Like what is the ratio of one error to the next? Okay, so because what I believe happened, and anyone who's done problem 2B can verify that it really does produce fourth order accuracy in that case. But might kind of fall short in this case. Actually, I'm looking to see if what else we have. Okay. Oh, that's okay. That's not the deferred correction stuff. Okay. Let's see. Oh, okay, those are our problems. Let's see. Okay. But anyway, afterwards, it'd be good to take a look at that. All right. So, okay. Now, oh, and I see that I have not all, but several of the students that I meet with on Mondays and Wednesdays here. Just to make sure you're all aware, I will not be around tomorrow because of fall break. So, okay. So I'll be after today. I'll be traveling for the rest of the week.
So in other words, send you all of our questions tomorrow.
Perfect. Yes. Well, still answer them, just not quickly.
Every time I get an email response from you for like 2 o'clock in the morning, my response is always like, does this man ever sleep?
I try to minimize that because I'm one of those people like sleep is time. Sleeping time is time I could be doing something. Whether it's something is important is another matter.
I feel that way, but like I can't act on it. Like I'm going to sleep.
Yeah.
So.
Okay. Yeah, I've become pretty good at resisting that. Okay. Now, all right. So that's for what I intended to cover today, which actually I think I still can fit in. Okay.
I have a few more questions.
Oh, yeah.
For number 2D,
D.
when you said change the right hand side, we're still solving the original problem, just the right hand side changes, right?
Right.
Because you said report on the error, and I feel like if we're just changing the right hand side, then the error should still be on that H squared.
Sorry, what?
If we're changing only the right hand side,
Yeah.
the error should be on the H squared.
Well, if I look at what's meant to be changed, okay, and it's refreshing my memory as to what that is. Okay, so what's happening here is the function f is discontinuous. So the error term in this case, it depends on so for a normal second order scheme, the error is minus h squared over 12 times the fourth derivative of u, which relates to the second derivative of f. But what if f doesn't have a second derivative? So it's not entirely clear. Like so if I had you change to a different f that was nice and smooth, then yes, you should definitely expect second order accuracy again in this case. But Not necessarily in this case.
Like,
That's still a possibility.
yeah, because I actually go second order.
Okay, so.
I just thought it was supposed to be second order.
At most, yeah. But because it may be possible to, because here's something else to think about. Okay, if a function f in this case is defined to be 1 for x greater less than or equal to 1/2, and then 0 after that. So there's a jump. The thing is, you're on a grid, and so what you could think of what your numerical method is doing is treating this as a function that is still smooth. It just has this abrupt change. But because you can define a function that descends in a smooth way from 1 to 0. So a function like that would still have a well-defined second derivative. That second derivative may be larger, but would still exist. Now, one thing that would be interesting to check is what would happen if you use that same scheme with a larger number of grid points? Because in that case, if numerical method is essentially treating this right-hand side f as a smooth function that descends abruptly from 1 to 0, it's going to look more and more like a function that has a jump discontinuity as you use more and more grid points. So it's possible that the second order accuracy that you're seeing now with maybe not too large a number of grid points might pose problems as h gets smaller. Now, off the top of my head, I don't know. But, and then if you were to go back to the other problem, the original f, that's a smooth function, and use that same large number of grid points, I wonder if you'll see different behavior in that case. Based on what I know about the error formula, it's something that could happen. Just because, so my colleague from Stanford, Marco Garrison, was a big believer in low order schemes, at least for the kind of problems that she deals with, where solutions tend to behave pretty badly. They tend not to be smooth. Because we also have other researchers who are a big proponent of high order schemes. But high order schemes really are only high order if a solution is sufficiently smooth. Why? Because people tend to focus in these error formulas like, okay, what's the power of h? Is it h squared? Is it h to the fourth? Yes, that's important, but what is that power of h multiplying a high order derivative of a solution? If a high order derivative doesn't exist, then do you really have that high order of accuracy? Not really. Now, doesn't necessarily mean that whatever problem you come across is necessarily going to expose that deficiency, but it's something that's worth looking into. All right. Okay, and then so here, okay, so you still got second order accuracy when you tried the first approach. But what about the various methods that are supposed to deliver fourth order accuracy? Because also, the higher order of a method, the higher order derivative the error depends on. So if you have a function that has, like an f, that has, say, 2 continuous derivatives, second order scheme be just fine. But if it only has 2 continuous derivatives, and then you want to use a fourth order scheme that would depend on a higher order derivative of f, then you might have trouble. But yeah, it's for a given f, higher order schemes will be affected by any bad behavior in f to a greater degree. All right. Any other homework questions? Okay, it has to be the last one because I do have something to cover.
Yeah, number 5.
5. Dang.
Good.
Well, okay, well, even so. Uh,
Notes, find the solution, what about computer exact solution?
yeah.
I'm wondering how we're going to do the analysis.
Oh, right. So in this case, well, okay. The kind of error analysis where you're actually computing the error and like doing a plot, that you cannot do. But just to like a theoretical error analysis based on Taylor expansion, where you're using like a certain finite difference formula for UXX and one for UX, and figuring out the accuracy scheme, kind of like in problem 2A, that you can do. As far as how the two methods behave, so finite difference in part A, finite difference and then Chebyshev in part B, really all I'm looking for is, for both methods, what happens to the solution as you increase the number of grid points. So start out with not too many and then increase it from there. And what happens, because of the nature of a problem, and what the exact solution looks like, you're going to see some bad behavior in both cases, unless you use enough grid points. So if you can get a solution that behaves well using fewer grid points, that's the preferable method. Okay. All right. Okay. So here, as I have been recently, focusing on just the AX equals B part. After you spatially discretize your PDE and get to an AX equals B problem, and what are the methods that you can use to solve it. So this category of methods has been seen in, like, it's covered in Math 561. But I'm not going to assume that since that doesn't apply to all of you. Okay. Now, so let's suppose that, using the same notation as earlier, x hat be my notation here. Okay. The exact solution x equals b, and then just plain old vector x is the approximation. So what that means is the computed solution is equal to the exact solution plus some error. Now, when you go ahead and get your approximate solution, you don't know what the error is. But a way to get an idea of what the error is to compute the residual. R, which is B minus AX. Okay, so because ideally, if the residual is small, hopefully the error is small. Although whether that's really true or not depends on the matrix A. Is it well conditioned or ill conditioned? So from AX hat is equal to B, if I now rewrite the exact solution in terms of the approximate solution, now I have A X hat minus E is equal to B. Oh, sorry, that should just be approximate solution. Okay. Then, okay. So now I'm going to rearrange this. I'm going to move. Actually, what if I to reconsider how I define error? So yeah. Okay. Dang it. Okay. So exact solution is approximate solution plus error. So this would be a plus. Okay. So now I have AE is equal to B minus AX, but that's a residual. So this is a very important equation that relates the error and residual. AE is equal to R. So that's going to become important to us a little later. So I'm going to put that up here. So I can refer to it later. So, as a result, suppose since the error is E is equal to A inverse times R, you could have a situation where the residual R is quite small. But then the error is still large. So multiplying R by A inverse could have the effect of amplifying that residual in giving us the error. So don't be fooled. Don't assume that just because the residual is small, that the solution is necessarily accurate. Oftentimes it will be, but don't just assume. Okay. Dang it. Okay. So now what I want to do is keep this idea in mind for developing an iterative method for solving AX equals B. Okay. So if AX equals B, what I'm going to do is I'm going to rewrite this equation as identity minus A, all times X is equal to B. So now I have, if I take this part and move it to the other side, I have X is equal to identity minus A x plus B. So then what I could do with this, since the exact solution satisfies this equation, I could think of this as like what's known as a fixed point iteration. Because I've now written an equation that the exact solution x is a fixed point up. So a fixed point iteration is something in the form x equals g of x. So this whole right-hand side is my g of x. So now I can write my iteration. Xk plus 1 is equal to identity minus A times xk plus B. So what I could do is make an initial guess for x, plug it in here, get my next iterator, keep what's called successive substitution, and hopefully this will converge. But at this point, I have no way of knowing if this iteration is going to converge. In fact, it may very well not. So what I want to do is try to come up with a way to ensure convergence. So I'm not going to apply this iteration directly to this problem. Instead, I'm going to take into account something I mentioned earlier, and that is preconditioning. All right. So I'm going to consider a right precondition problem. So A P inverse Y is equal to B. So X is equal to P inverse Y. So that's how, so I'm basically making a change of variable. Oh, thanks. Okay. All right. Now, so I don't know if I was disturbing people out in the hall or okay.
Yeah, they just get kind of loud over there.
Oh, that's true, yeah. Okay. Yeah, we do. Okay, so now what I'm going to do is I'm going to take this iteration and apply it to this system with this matrix. So now what I have is y k plus 1 is equal to identity minus AP inverse yk plus b. The idea being that if P is chosen well, that maybe this iteration can be made to converge even if the original one would not. The question is, how do you choose P to make that happen? So we're just trying to be a little more flexible here, because P has not yet been specified. Okay. So now what I'll do is I want to rewrite this iteration in terms of x. So all right. So I'm going to multiply both sides, but on the left by P inverse. So because P inverse y would be x. So this would be xk plus 1. And okay. So now I've multiplied everything by P inverse on the left. Well, this right here is just going to be xk. And then I have minus P inverse A, P inverse yk, that's xk again. And then I have P inverse B. Okay. All right. So now, and I apologize for my horrendous board use. I seem to get myself stuck in that regard. So now I'm going to rearrange this. I have xk plus 1 minus xk. So I'll move this to the left. And then what I have is P inverse B minus AXK. But how can I more simply express that right-hand side? What do I have on the right side? Residual. And you can think of this as, it's not exactly the error, but it's the step you're taking to improve your solution. So we have, so I let dk equal xk plus 1 minus xk. I use D for direction. It's a step we're taking from one iterate to the next. So then I have the following. P times dk is equal to rk. All right. So let's compare this equation and this one. Both cases, residual on the right-hand side. Left-hand side, we have some matrix times basically how you're trying to correct your current solution to get your improved solution. So here we have the actual error. Here we have what's hopefully an approximate error, because but we'll just keep doing this to try to get rid of all the error. Because this is supposed to go to 0 because the x's are supposed to converge. So we again have a situation of matrix times error is residual. But in both cases, we're trying to solve the same system. We want to solve AX equals B. So since this is how the residual and error actually relate, but here's how they approximately relate, this gives us an idea as to what kind of P we should choose. So how should we choose P? So that this is an effective way of solving AX equals B. Because we want this, we got this. So what should be true of P to be a sensible iteration for solving AX equals B? So I could pick P to be anything. Anyone? It's all about the relationship between these two equations. So for example, if I didn't do any preconditioning at all, that would be the same as choosing P equal to the identity. And that's basically saying that the error is a residual, which we know is not true because of that. It's okay to guess. Well, not inverse, but but just A. Like if I chose P equal to A, that would work. I would get the error, and I would correct the solution to get the exact solution. Now, that's not a practical choice. I'm not saying that. But, and so I don't know if that was a point of hesitation for some of you.
Yeah.
Okay. Say it anyway.
Well, I thought P equals A, or
Yeah.
P equals A is numerically complex.
No, it's not. But yeah. So the thing is, it's better to illustrate the thought process. Put the thought process out there, including reservations, and so then I can see what's going on, as opposed to dead silence. Okay. So, yeah, it's definitely not a sensible choice because that's the system we're trying to solve in the first place. So now, if we look back at our iteration, this is our iteration. It requires solving a system involving P. So this leads to the same criteria for preconditioner that I mentioned before. You want P to be an approximate A, but you also want solving systems with P to be easier than solving systems involving A. And whether you can find a preconditioner that meets both criteria, it depends. So for certain classes of matrices, it's not hard to do. Okay, so if we can't choose P equal to A, if we can at least get some criteria for how good an approximation P has to be, then that's still something that's helpful. So now we'll focus on doing that. So then we look at, under what circumstances does an iteration like this even converge? Any questions about the manipulations that happened here before I erase them? Okay. Now, okay, how to find error earlier? Oh, I erased that. Dang it. Okay. Now, okay, so what I want to do is return to okay. Oh, yeah, I need to work with iteration in some form. I guess I can work with that. What I'd like to do is see what happens to the error as k goes to infinity. Okay. So given the iteration in the simplest form in which I have it written, P xk plus 1 minus xk is equal to residual P minus axk. I can find the error ek to be the exact solution minus the kth iterate. So how does ek plus 1 relate to ek? Because if I can show that there's some relationship between the two where ek plus 1 is definitely going to be smaller than ek, then I'll know I'll have convergence. Because I can say as k goes to infinity, the error is definitely getting smaller, it's going to go to 0. So now we have to return to this and see how to do that. Okay. So first I'll do some distributing. Now I need to introduce the exact solution. Oh, use a hat here so that should. to get a handle on error. Okay, so for that purpose, well, for one thing, B is equal to AX hat. So now what I have here is I have A times X hat minus XK. So now I have AEK. All right. Now, okay. If I subtract from both sides, Px hat okay. Well, now I can factor out p's. So now I have minus p ek plus 1 is equal to minus p ek plus aek. So now what I can do is solve for ek plus 1. So ek plus 1 is equal to identity minus P inverse A times EK. So that is how the error changes from one iteration to the next. So at least we have a nice simple relationship. So since the error at each iteration is just a previous error times a fixed matrix, so to get the error over many iterations, I'm just going to keep multiplying by this matrix. Then that gives me a sequence of errors. How do I know whether those errors are going to 0? So I won't get into all the details here, but so EK goes to 0 as K goes to infinity if, and there's actually two conditions that I can give. If the norm of identity minus P inverse A is less than 1. So if it's some norm, whether it's one norm or infinity norm or two norm, if you can show any norm that matrix is norm less than 1, that is sufficient, it will, the error will go to 0. Another condition, if and only if spectral radius of identity minus P inverse A is less than 1, so necessary and sufficient. And this is because any norm, any natural matrix norm, is greater than or equal to the spectral radius. So you get a situation where various norms are greater than or equal to 1, but if the spectral radius is less than 1, it still works out and you have convergence. And then we can see why. If you chose P equal to A, this matrix would be 0. That's the idealized impractical situation. If P was at least a decent approximation to A, you can see how this matrix would perhaps be small and therefore meet one or both of these conditions. So this gives us at least some guidance on how to choose P to get a convergent iteration. So questions on these manipulations? Okay. Here are some specific well-established choices of P. This assumes a breakdown I gave before. A is equal to L plus D plus U. Lower triangle plus diagonal plus upper triangle. So all these preconditions are defined in terms of those pieces. Simplest choice, P is equal to D, just the diagonal part. This is known as the Jacobi method. This is, so this converges if A is known to be diagonally dominant. Actually, I'll check my notes here. Okay. There's certain conditions for convergence. I know I should remember these things off the top of my head, but it just doesn't happen. Okay, so section 5.1 of my book is where these methods are covered in more detail. I did not cover that section in 610. Okay. Okay. As far as proofs about these things, did I mention this in here? Okay, got it. I know I'm short on time. All right, number 2. P is equal to D plus L. So we throw in the entire lower triangle, including a diagonal. Now, both these choices, the system involving P is easy to solve. Diagonal in this case, lower triangular in this case, so it takes less work than solving a system involving A. This is called the Gauss-Seidel method. It turns out, even though this is diagonal and this is lower triangular, the two methods actually take the same amount of work. The reason for that is what's carried out for Jacobi as part of a matrix vector multiplication is just shifted into here as part of the forward substitution process. So the operations are they're not exactly the same, but the amount of work is the same. In fact, you can derive Gauss-Seidel from Jacobi just by using the most up-to-date information about xk plus 1 to compute later components. And this is known to converge if also diagonal dominant, just like Jacobi, and if it's symmetric positive definite, it will converge. And finally, P is equal to D plus omega L, where omega is a relaxation parameter that must be strictly between 0 and 2. This is called SOR, which stands for successive over-relaxation. And since, everyone here in the room is or is about to be a PhD student, I will tell you that SOR was developed in 1950 by David Young for his doctoral dissertation. Just to make everyone here, including myself, feel like schlubs. And you can actually download it. It's thankfully been LaTeXed up. I mean, LaTeX did not exist in those days, but when I was looking through it, I found something that looked like it might have been a mistake, but but the method works though. also converges if certainly if A is symmetric positive definite. I can't recall off the top of my head if it's always convergent for diagonally dominant, but it probably is. Okay. There's a variation of SOR for symmetric matrices, SSOR, so symmetric successive over relaxation. So the idea is to try to choose a parameter omega to speed up convergence. So if omega equals 1, it's just Gauss-Seidel. Usually you want to choose omega between 1 and 2. For certain classes of matrices, it actually is theoretically known what an optimal omega is. All right. So those are some of the best known choices. But as I said, preconditioning in general is still a very active area of research. Normally for other types of iterative methods, like Krylov subspace methods, like a kind that I did cover in 610. But now, those of you who took 561, you did learn about these methods, but I did not talk about them from a preconditioning point of view. But now you have this additional perspective. So ideas for preconditioning can be used for these kind of stationary iterative methods too. All right. I should point out for the general fixed point theory, if x is equal to some function g of x, I'm being sloppy here, but among the sufficient conditions for convergence if the Jacobian of G would be a matrix if it is less than 1 in some norm. So in this case, the Jacobian, which is basically the first partial derivatives of G, is exactly this matrix here. Identity minus P inverse A. So this is just a special case of, and this is for nonlinear equations that can be written in fixed point form. Here we have a linear equation, but certainly that same theory would apply. Fixed point iteration I cover in 560. Well, so a number of you have seen that. Okay, so and that's a very interesting area in its own right, because it's a very powerful tool for solving all kinds of difficult equations or simple equations like this one. Okay, so methods like Jacobi and Gauss-Seidel are important ingredients in another approach to solving systems that come from PDEs called multi-grid methods, which is the subject of homework problem number 6. And that's what I will be covering when we're back from the break. Okay, so that's all. But I'll deal with any questions for anyone who sticks around.
Our next class is Tuesday.
Right. So.
I mean, if you want to come here Thursday, you'll be the only one here.
I'm wondering if we have to come Tuesday.
What?
You might still be traveling, I wanted to mention.
Oh. Well, that's not part of the plan, but we'll see.
That's when the class will be online.
Yeah.
Okay, well, enjoy the break. Hope you actually kind of get one.
Oh, I am not doing anything on Thursday. Everything has been going crazy since the semester started, and I just need a day. Yeah.